Oh, wacht even. Er gaat iemand... Oké, die is nu gemute. Oké. Thank you all for joining this version of the Circular Industries talks. Today we have with us Estelle Gervais. She works at the Fraunhofer Institute for Solar Energy Systems, but is also a PhD student at CML Leiden University. And today she will be sharing her insights if it comes to the supply chain for photovoltaics and talking about secure and responsible supply chains. So without further ado, Estelle, the floor is yours.
Thank you. Yeah, well, hello everyone. I think René said it all, so I'm going to present to you some of our results on supply chain risks in PV related to security and responsibility. So to put the topic into context, I think you know that PV is expected to be a pillar of the energy transition. You can see on the right the projected cumulative installed capacity by 2050 in a 100% renewable energy system model. So this over 60 terawatt peak PV by 2050 is to be compared to around 1 terawatt at the end of 2022. So a huge growth for PV is expected, or rather required, which raises questions for supply chain risks. So there are different types of risks. The first one would be pace and scale of growth. Can supply keep up with demand in terms of quantities, in terms of timelines? Then supply concentration. Is there an over-reliance on suppliers, and if so, where in the supply chain? And finally, ESG due diligence. So are there environmental, social governance issues that could cause supply disruptions? So today I'm going to focus on these two last points. I think there are quite some publications out there on PV material demand from us, from others. So let me dive into an overview of the PV supply concentration. So here you can see the main supply chain for PV from quartz mining to PV module assembly. Supply or production is highly concentrated in China from polysilicon to module. So wafer is the most critical stage. Virtually all PV modules that you can find out there have been processed at the wafer stage in China, and module is the most diversified stage. So it's the easiest one to reassure at the moment. You can hear every now and then some announcement in the EU, US of PV plant announcements, and most of the time it's for modules. Having recognized this supply concentration, there have been initiatives to diversify, most prominently the Inflation Reduction Act and the Production Linked Incentive in India. And in the EU, we have the Net Zero Industry Act, which goal is to cover 40% of PV demand by 2030 with local production capacities. Now, what's important to recognize also is that this supply concentration goes beyond the supply chain of silicon. It also concerns other materials. So for instance, silver. So here we conducted a market analysis to know where the silver for PV comes from. So silver powder is required, and this powder is then mixed into a paste, which is laid down or rather printed on the PV cells for metallization. And so as you can see, powder is for large part fabricated in Japan. There's actually only one company behind it, which is Dowa. And silver paste is produced in China. And it's actually not that surprising because as a silver paste manufacturer, you do not want to have to ship your silver across the globe. You have to be close to your customers, which are cell manufacturers, and these are in China. What's more interesting to look at is the company headquarters of the silver paste manufacturers. There are different types of pastes depending on the PV cell technologies that you are considering, but for the most standard paste at the moment, P-type front high temperature, China is here leading the market. And it's actually quite new. In 2016, China only had 17%, so 17% market share for this product segment. And what happened in these few years is that other manufacturers such as DuPont from the US or Samsung SDI from Korea exited this business and sold it to Chinese manufacturers. So localization is in full swing, I would say, for most paste types. The only exception is the N-type low temperature, which is used in heterojunction cells. And heterojunction cells are one of the most promising candidates, let's say, for next generation cell technologies which provide higher efficiencies. And here, Japan has the advantage at the moment. So the takeaway message is quite simple. Non-Chinese producers are not leading the standard paste market anymore. So supply concentration has been going on for quite some time in PV, but it's still ongoing and also broadening in scope. It also concerns web manufacturing equipment, especially for the ingot and wafer. For cell and module, it's a bit different, but for ingot and wafer, we had a master student, Oscar Ortega, who looked at the landscape of who is producing manufacturing equipment, and the findings were quite interesting. So to sum up, if you want to produce ingot and wafer, you need the main input polysilicon, but you also need access to all those secondary supply chains for equipment and consumables. So some of them are listed here, but there are others: chemicals, automation, cleaning equipment. And what was found is that there is no industrial capacity outside China for especially these four components: the high purity quartz puller, the Kowalski puller, the high purity quartz crucible, the graphite hot zone, and the diamond wire and diamond saw. And the reason for that is a technological and cost gap. So to put it really roughly, China has the most advanced technology, the best quality, and the lowest prices. So to be clear, there is some knowledge available in the EU to produce this component, especially the puller, for instance, knowledge from the semiconductor industry. And this could be transferred to the PV industry, but it's not quite straightforward. You need some years and money to be able to catch up with the current technology and the PV specificities. And then you need additional time and money to catch up with the prices. So you also need to have access to customers locally, would be optimal. So you need to have ingot and wafer manufacturers in Europe, for instance, which is at the moment quite difficult and limited. There are also specific issues, for instance, for the hot zone, which is made of graphite. The design of the hot zone is a really crucial part of this process, and there is a lot of business secrets on how to produce it. So not just everyone can start producing ingot wafer manufacturing equipment from today to tomorrow is what I want to convey here. And why is it relevant? It's relevant because China is considering restricting exports on this ingot and wafer manufacturing equipment. It's not quite clear yet if it happens, what would be the consequences for the reshoring targets, but certainly one way or another, this would have some kind of impact. So this was kind of the overview, but I think what's more interesting to look at is what does it mean to be really reliant along the supply chain? What is the risk exposure if there is a supply disruption? And to answer this, we used a really simple cascade failure model that you can see on the right. So we simulated export restrictions, and the way it works is the following. Imagine that country A reduces exports by a certain fraction alpha. The supply shortage spreads through its trade channel. But then each country has a certain crisis absorption capacity beta. So think about it as a stock or inventory or buffer capacity that you can activate on a short term. So each country can either absorb the crisis or has to transmit it down to its own customers. So we simulated export restriction from each countries and from each process step to kind of compare them. And the way we describe it is that each supply disruption has a damage function that you can see here on the right. And we introduce a metric, the fragility ratio, which is the slope of this curve. And it really just simply quantifies the potential downstream shortage resulting from a supply disruption of a certain magnitude. So for the case of the PV sector, the fragility ratio would quantify the percentage of PV deployment at risk. Here are the results that we obtained for the business as usual scenario, so 2021 supply chain. And the way to read this heat map is the following. Imagine that China decides to ban wafer exports. Then it means that 61% of US PV deployment would be at risk of failure, would not happen. And the conclusions here are that the EU and India have kind of the same profile. They are dependent on the end product. Without Chinese modules, it's kind of a no-go for PV deployment in these regions. But it also means that the EU and India are not exposed to upstream supply disruptions. If there is an export restriction on quartz, silicon metal, polysilicon, it would not have a huge impact on PV deployment. And that's because there is a high degree of vertical integration in China. Not the same can be said about the US. Cell and module procurement is already quite diversified. As you can see, the US buy their modules mainly from Vietnam, Thailand, Korea, Cambodia, etc. But these countries in turn are still highly reliant on Chinese wafers, so that a wafer export restriction would still hurt the US down the line. Another finding is the small number here. What it means is that if China decides to restrict exports on metallurgical grade silicon, it would hurt 7% of its own PV deployment. And this kind of backfiring effect is due to the network nature of supply chains. So in this particular case, what happens is that China exports metallurgical grade silicon, a part of it, to Malaysia. Malaysia produces polysilicon out of it and exports a part of this polysilicon back to China. So this is really the interdependency that you have going on, and that could result in this kind of backfiring effect. So probably in more complex supply chain, this is something to be considered if you want to avoid unintended export restrictions impact. So another question that we wanted to address is what would happen if the EU, US, and India do manage to diversify supply and turn towards friendshoring especially. And to answer this, we need to model friendshoring, which is really not that straightforward because it's kind of the buzzword at the moment with no working definition in policy context. You would hear some statements about we need to procure more from like-minded countries, from trusted countries, but from a methodological perspective, it's not quite clear yet how we identify these countries. So here's one proposal, at least, to model friendshoring. The way we did it is by using a differential evolution algorithm, which finds the best combination of trade relationships to minimize the disruption potential. So to say it quite simply, what the algorithm does, it's Python-based, is to find who should supply to whom in order to minimize the risk of market concentration, the risk of governance issue from the suppliers, and minimize the risk that a good is being sourced from a country which is not willing to supply to another country. And this definition here is actually largely based on the work from Nassar and colleagues. Especially interesting is the willingness to supply index, like how do you quantify how willing a country is to supply to one another? In our case, we used 3 components. How much two countries trade with one another, with the rationale behind it that if they trade more with one another, they are more willing to supply to one another, whether they are in a conflict or not. And finally, shared values. So how aligned are two countries on foreign policy and global issues. And to quantify this, we used the UN General Assembly voting data. These voting data are actually quite used in research on international relations. And the reason for that is that this General Assembly is the only assembly where all UN countries are represented and get to vote on human rights, Middle East conflicts, or nuclear weapons, for instance, and they get to vote yes, no, or abstain. And it means that it's possible to assign a score to each country representing its voting behavior over the years. This is what you can see here on the right for selected countries. And the way to read it is that, for instance, if the distance between the scores of two countries is getting higher, it means that they tend to not align on this specific resolution. So you can recognize, for instance, such trends as during the Cold Wars between the US and Russia. You can also recognize some patterns of bloc voting, for instance, within the Global South or within the EU. So really briefly, this is kind of the theoretical background behind friendshoring. And here are the results that we got from it. Reshoring targets are included in the scenario. And what can be seen here is that the risk exposure of the US and India is largely reduced compared to the business as usual scenarios. You have no export restriction that would hurt more than 20% of US PV deployment in this case. It's not the case for the EU, which still shows a fragility ratio of 65% for Chinese module. And the reason for that is that friendshoring and over diversification is not about eliminating risk, it's about transferring risk, either locally or to other partners. In this particular case, the algorithm assigned this risk to the EU because the willingness to supply index between China and the EU shows a lower risk than the willingness to supply between China and the US and China and India. And someone has to procure from China, right? Because it's a main PV supplier and will remain it for the next years. Right, so friendshoring can mitigate risk to a certain extent, or at least for certain countries. What about recycling? So here, it's important to know that to recognize that closed loop recycling is not a guarantee for supply security. I think it's quite clear when you adopt a supply chain perspective that, for instance, if you do manage to recycle silicon from end-of-life module back to polysilicon, which is not a given first, but you still need to ship it back to China for wafer manufacturing, then your supply security benefits are quite limited. Similarly, if you do manage to recycle your silver from end-of-life modules, you can see here on the right where it's located, but you still have to ship your silver back to China or another country for paste fabrication, where your supply security benefits are also quite limited. So the supply chain perspective is quite important in this assessment of recycling benefits. And finally, I would like to touch upon the ESG due diligence, which is a growing topic, especially in the PV industry. The background of it is that there are social risks in PV. For the past few years, there have been quite a number of reports from civil society researchers of state-imposed forced labor in the province of Xinjiang, China. And according to these reports, around 1/3 of global polysilicon and metallurgical grade silicon, which are used in PV, are produced in this province and would be linked to forced labor. So there have been quite concrete measures against it. Most prominently, the US WIGO Forced Labor Prevention Act. Under this act, more than 2 gigawatt PV have been denied entry on the US. So this is quite a clear example of how ESG issues can limit supply availability. And most recently, the EU has approved or has almost approved a regulation on products made with forced labor. And the way it works is that the EU will provide a database over the next year with a list of products and countries associated with forced labor, and most probably PV modules will be a part of it. So something that we have recognized in the PV industry, at least, is that risk-based due diligence is increasingly required. So companies are required to conduct supply chain mapping and ESG risk assessment for their supply chains. There are, however, no standardized methods to do so. So I think this is where industrial ecology tools come in hand. And this is what we did on the supply case of on the case study of silver supply chains for PV, trying to do a risk-based due diligence. And the way it works is that first you have to do the supply chain mapping. Material flow analysis can be used here. You can see here on the right the results that we got from silver, from the mining to the module manufacturing. And these are most probable supply routes. These are not verified supply routes, but most probable ones based on trade data, among others. And we found that 30% of the silver used in PV, it probably comes from one of these routes. And it's quite interesting because we found that a lot of it is being refined in Korea, which is surprising because Korea actually does not play a significant role on the global scale for silver refining. It's really a PV sector specificity. And once you have these supply routes, you can assess the ESG risks by country. There are a few databases out there for it. We use the Environmental Performance Index, the World Governance Indicators, and the Social Hotspot database. And so here are the results that we obtained for silver in PV. What you can see is the percentage of silver in PV associated with a given risk. So for instance, 94% of silver in PV is associated with a very high risk regarding voice and accountability. So we found that more than 85% of silver in PV transit through countries with very high ESG risks for voice and accountability, water resources, biodiversity, occupational hazards, social benefits, excessive working time, and child labor. So these are risks, not verified ESG issues. It's also on a country level and not on a company level. So really what this assessment is about is providing a third party neutral assessment of the risk and provide a basis for companies to know where to look, where to conduct on-site due diligence to monitor the real situation, I would say. So to conclude, I think it's quite clear from the current supply concentration that PV supply chains will remain global. There will be interdependencies, and probably there should be interdependencies anyway. And there is a discrepancy between the political agenda for resilience and the current reality of EU PV reshoring. So, right, on one hand, you have this target from the Net Zero Industry Act, 40% domestic production capacity. But on the other hand, it has not translated into really positive signs over the last year in the EU PV industry. At least we saw a lot of alarming headlines of EU PV manufacturers having to shut down, having to lay off, or moving to the US, where the financial situation is not the same. Industrial ecology has, I believe, a bigger role to play in all these challenges to provide an overview of security issues in supply chain mapping, and also ESG due diligence. So material flow analysis is the dedicated tool to do that, I would say. And there is also the question of diversification. Diversification is wished for from policymakers, but I think there is still quite of unanswered, unaddressed questions that industrial ecology is quite well placed to address. So for instance, what form of diversification do we want to achieve? Do we want reshoring? Do we want friendshoring, or a small buffer capacity for extreme events? And also, how much diversification is realistically achievable? So these are all probably interesting avenues of research, I would say, for the next years. So this concludes my talk. Thank you very much for your attention. And if you have any questions, please feel free.
Thank you very much, Estelle. I'll give you a real hand, and maybe there are some virtual hands, but thanks for taking us with you in this interesting quest related to supply chains of PV. Yeah, I think it's interesting to see. I think you highlighted for me some interesting things. I have certainly some questions about, but if you have any questions, please either raise your virtual hand or open your microphone. I see Peter.
Yes, hello. Thanks, Estelle, for the um, uh, all the reflections on the silicium-based solar panels. There are also developments in thin film PV production. Can you elaborate on your view on the situation with regard with thin film PV industry?
Yeah, thin film is an interesting topic also. So in the past we had CIGS, cadmium telluride, and CIGS is kind of disappearing right now. I would not say that it's a really relevant technology at the moment for PV, especially with the lower efficiencies that they got. Cadmium telluride is certainly there to stay. I mean, they are backed by First Solar in the US, which has a lot of wind at the moment with the Inflation Reduction Act. So certainly this technology will have a role to play, but it will probably remain at a niche market level as it has been for the last years, I would say. A few percentage of the global market shares. But certainly what's really interesting at the moment is perovskite. Perovskite has attracted a lot of attention because of this high efficiency. And this is, from a supply security perspective, a technology where the EU has a card to play. We have a lot of actors here, research, but also industries working on this topic. I mean, the whole world is working on it, right? But I think we are still really competitive on this topic. We have Oxford PV, we have others. So here, certainly perovskite will have a role to play and has the advantage of using other materials. Still, there are some materials in it that we have to be aware of. Indium, for instance, and I think it's quite known that we need to reduce indium production for perovskite to be scalable to terawatt capacities. But for the rest of it, it's a lot of abundant, or let's say available materials, and there is still industrial capacities in the EU to have them available. So this is kind of the maybe a light for hope, I would say, for the next years in this context.
Thank you.
I think also if you look at nanosolar and what they're doing in the US, I think the only reason nanosolar is still alive is because of basically protectionistic measures from the US government, else they would never be able to compete to Chinese solar producers. So that's an important thing, I think. And I think for perovskite, I think also a lot of the attention is now going to using perovskite in tandem, let's say, with regular. It's on top of, let's say, regular solar cells. Yeah.
Yeah, exactly. It's kind of the natural way to go because we have all these silicon production plans. So you have to make the transition, and then later on, maybe we will have perovskite, or even triple junction. Yeah.
Perrine.
Yes, thank you so much for the presentation. It was very interesting. I have a comment and a question. The comment is on your on what you said with the 40% regarding the net inflation. No, not the
net zero.
The Net Zero Industry Act. It's actually not 40% on PV. It's 40% on renewable energy. So I was at a conference a couple of weeks back, and yeah, the European industry the European Union is very adamant about emphasizing that it's not just for PV. So it is possible probably to meet those targets in that sense. So yeah, maybe just double check that. And my question is, when you were talking about the impact that the U.S. restrictions had on how much China was able to import or export, I'm curious if you think that these bans, based on the research that you've done, will have enough of an impact on China for China to act on, for example, the ESG issues that are being brought to light, or that have been brought to light.
You mean this Uyghur Forced Labor Prevention Act, right?
Yeah.
And
the one that's potentially coming up in the EU as well.
Yeah. I do think that it will have an impact because as soon as the US Uyghur Forced Labor Prevention Act was adopted, we saw a lot of announcements for new policy plans outside Xinjiang, right? So it happened really fast, and suddenly it was there was an announcement that it was going to be in Inner Mongolia, which also has its own issue, but still it's out of Xinjiang, right? So it seems like if someone can do it, it's probably China. React really fast on a really big scale. So technically, it's possible. And I mean, the EU and the US as one of the most the biggest markets for the future. So it seems reasonable to think so. Now, of course, you could say that they would move their plants to Vietnam, Malaysia, or whatever, but this would still be Chinese companies, and they would probably, or they could still have a link to Xinjiang. So there is a lot of discussions about how to ensure that we do not condone a supply chain that just has a company that for 50% supply to the EU with a certain supply route, but for the other 50% supply to the Chinese market from Xinjiang, right? So it's not quite clear yet how it's going to happen, but I think it's the best we can do at the moment with what we have. But to come back on your comment, I was not aware of that. That's quite interesting because it seems like really let down in terms of ambitions. But yeah, thank you for pointing that out.
Yeah, of course. Maybe double check it. I've checked it a couple times, but it was a big letdown for me as well. So
yeah.
Yeah.
Thanks. I see. Before I go to the hands raised, there's one comment that was earlier there in the chat by Misha Klarenbeek. He says, "I cannot currently use my mic, but where can we find those MFA graphs, such as the one for silver? It would be interesting to see them for more materials."
Yeah, the one for silver we published. I can send you the link in the chat. And for silicon, review is ongoing, I would say. But yeah, I do hope that there will be more material flow analysis in this sense. It's quite time intensive, but still doable.
Yes, thanks. Mark, you raised your hand.
Yeah, thanks for the presentation. I work for the province of South Holland on these kind of topics, and one of the things we're looking at is also recycling. You said that recycling could be a part of the solution to reduce our dependencies. Is there anything you can say about how much capacity we need for recycling and where this capacity, for example, should be placed within the EU?
I don't have specific numbers in mind, but what we have seen, at least at the moment, is that each country separately in the EU has not enough waste volume to have a big economic case. So there are really weird situations happening in the EU where some countries cannot or have to ship their waste to another country to have the economic waste flows for it. So there is certainly a lot of regulation work to be done here to allow, for instance, the waste flows among within the EU. So to achieve the capacities or achieve the economy of scale, and I would say anyway that it will not happen before 2030. So we would not have enough capacity before 2030, apparently, or this is what we calculated. I mean, China certainly has the capacity at the moment, but I cannot give you a really hard number on that, but probably on the middle term.
Yeah, I think it's also true that China is not only ahead in terms of the primary production, but also in terms of the recycling. That's true for many of these products as well, right? Also for batteries, I think that's certainly true. And interestingly, if you look at recycling as it's done now, I think that with what is normally done is that the aluminum frames are taken off and the glass is being recycled or downcycled often. And then the other parts are, well, that's basically lost. So the silver is not recovered. Well, it's an interesting element to recover. I think that what is done now is very limited, let's say. And that's also because, of course, well, the limited amount of scrap that is available. So that will change in the future. Design will also could also help if you would design solar cells differently. That would make recycling a lot more easy. But then again, yeah, since all these solar cells that we are using at the moment comes from China, so we would have to influence the Chinese producers to actually make that happen, or well, somehow. Stimulate European producers that might be able to do that. But I think that we've recently done a study for PBL, for Planbureau voor de Leefomgeving, on recycling of batteries, PV cells, etc. And one thing that you see in all the discussions that we had is that, well, there's two goals. There's the energy transition goal, and then there's the circularity goal. But the energy transition goal is there, and the circularity goal is somewhere there. So that really comes second. And you can imagine why that is true. I mean, this energy transition is really important, and everybody's focusing on that. But yeah, we basically lost track of the circularity goals in that sense, and that's kind of a pity. Yeah.
Yeah, in the PV industry especially, there is a strong focus on recovering materials, but from a supply chain perspective, it would make sense to recover the wafers, right? But there is no economic case for it at the moment. No. It's also more difficult, so yeah.
Yeah, I mean, there's a Dutch startup, for example, that makes a recyclable and reusable PV solar cells, but that's of course, yeah, still in a very early stage of development. Yeah. Okay, I don't see any other. Oh, there is Perrine.
Yes, sorry, thanks. Yeah, I'm working for one of the startups working on circularity for like a better design. And indeed, we're still in the early stage and there's so many challenges, but it's moving. I have a question regarding sourcing of the data for these MFAs, because what we noticed was it's sometimes very difficult to find, to just find the data. And I'm wondering how you tackled lack of data, if you did come across that.
Yeah, of course. I think it's a must at this point, right? Yeah, so for silicon and silver, we have the chance that there are trade data for the primary materials. So at the ore and refined stage, you can find trade data, which are pretty good. Also for PV cell and PV modules, since 2023, they have separate trade numbers, HS code, which is quite new. So it's really helpful in this sense. But then the whole middle stream is so difficult to map for all materials that we considered, because we have also mapping ongoing for nickel, for perovskite, actually for perovskite materials. So for nickel, lead, etc., it's incredibly difficult. So we have found no other solution that than complementing this trade data with market data. So we conduct interviews. Also really helpful is looking at investor reports. So if you look at the IPO reports, sorry, most of the time, companies, Chinese companies, also indicate who their suppliers are, so you can kind of try to fill the gap. Also, a trick that we found is really helpful is doing the research in the local language. So you have to look at it in Chinese or in whatever language it is, and you will find way more data. And it's kind of this investigation work that you need to close the gap for the middle stream. And we have not found anything better, and I'm not sure it's possible anyway, but it's also what OECD due diligence regulation or guidelines advise to do, trying to rely on this kind of reports and indirect data. So it's an imperfect solution, a lot of uncertainties. That's why I try to talk about probabilities of trade routes, but give some kind of insight is what I want to say.
Amazing. Thank you.
Thanks.
Thanks.
I don't see any questions in the chat or hands raised. So with that, I would like to very much thank you, Estelle, for presenting your work here. I think it's very interesting, and of course I've seen some of that before. But I think it's a really unique way of looking at these supply chains, and I've never. I think you did something that is not out there yet, and I think provides insights that could also. Well, it would be very hard to generate them in any other way. So I think it's really really useful work. So thanks for sharing that with us today in this event of the Circular Industries Talks. Thank you all for attending, and hope to see you all next time.
Thank you very much.
Okay, bye bye.